Usually helps. Right? All right, there we go. All right, everybody, welcome. So Jim's Called to Craft Beer started with his first pint of Bar Harbor Real Ale at Lompoc Cafe in 1991. That one pint led to 26 years of being in the brewing industry, manning water tuns from 5 to 35 feet across. Jim is currently a partner at Meliora Partners, which is a continuous improvement consulting firm, and he lives in the past. Today's presentation is meant to be an introduction to control charts and how one might use them to make better quality beer. Welcome, Jim.
Thank you, sir. Thank you very much. A couple caveats, not a public speaker, so bear with me. We also, when we teach, I do teach a little bit as part of my job. It's a little bit more interactive, kind of back and forth. So honestly, if you guys have questions or want to interject, that's fine with me as long as the moderator doesn't tackle you. And so we're not used to like one-way communication. So I built this deck to kind of show you some stuff, but please, if you have questions, throw your hands up. All right, let's get into it. Introduction, the only reason I put my resume up here is so that you understand I did work in the brewing industry for a bit. So I did actually use these tools in brewing. I found them to be useful, and I'd like to share a little bit of my experience with you. I did 20 years at a small brewery in a couple different stints, from running the restaurant up to running the brewery. Did 6 years at North American Breweries or FIFCO or NAB or High Falls, whatever you want to call that brewery. I worked there for a while. While I was there, that's when I was able to get my Six Sigma black belt thing, which is how we got into all the statistics. So that was a nice opportunity. And then the last 4 years, I've been with a company that does continuous improvement full time. So we work with a lot of companies working through business problems. Part of that method is to bring some statistical tools to look at their data. So the intent here is if you don't use control charts or something like that to control, monitor your processes in the brewery, this is an introduction. If you are a math ringer, and I'm looking at this little section over here, this will be introductory for you. Oh, and last thing, Meliora means, it's Latin, it means ever better. That's the name, that's what that means. All right, that's it for that. My goals, it's easier if I can see here. Oh, it happened again. Okay. My goal is that you walk out of here knowing what a control chart is, what they are telling you, how you can use them in the brewery. I want you to understand the difference between continuous and discrete data so that we're using the right data. Understand what the voice of the process is, which is what control charts are. And understand, this is the most important thing I want you to walk out of here with. What is the difference between common and special cause variation? Okay, because that's going to tell you when to act and what to do. And we're going to talk about why that's important. If you know me, I'm allergic to any meeting that doesn't have an agenda, because that's what makes for crappy meetings. So this is a meeting whether you like it or not. So I have an agenda. We're going to talk through the what, why, and how. So the what is the types of numerical data variation. We're going to look a little bit at frequency plots, how to make them. So we're going to talk about data normal distribution. You're going to need to know a little bit about that to do control charts. And then control charts themselves. The why, we're going to talk about the types of variation, the appropriate response to those, and what tampering is, and why you're not going to do that anymore. No more tampering. And then we'll talk a little bit about how I did walk through how to do some of this in Excel, whether that's useful to you or not. I know it's something you can Google, so it's not going to be an hour of Excel-based learning at all, but I'll show you the steps, collect and enter your data, create a histogram, calculate your basic statistics, and then make a control chart for yourself. Anybody here use Minitab statistical software? Okay, perfect. That's what we use. It takes about 2 seconds to make a control chart Minitab. Unfortunately, it's about $2,000 a year for the license, so nobody has this software. So I'll show you how to do it in Excel real quick. Okay, here's the problem statement, the question. So when I was a brewer, before I did any of the math stuff, by the way, in high school, I hated chemistry and math. Then I became a brewer, which is essentially chemistry and math, right? So congratulations to me. I had to catch up on all this stuff. So in the brewery, I have really the fundamental question, keep coming back to, is do I need to adjust my process? Do I need to do something with a runoff? Do I need to do something with my pitch rate? Whatever the question is, the value of interest, whatever you're trying to figure out, do I make a change or not? That's really one of the fundamental questions. So in the brew house, we've got yield and efficiency, fill levels, your OG. We're data rich, right? We've got data all over the place. The question is, how can I use that to decide Do I need to make an adjustment or not? Before I knew much about statistics or math or any of that stuff, I found a clue in the Practical Brewer. So you all are Master Brewers of the Master Brewers Association of the America members, is that correct? MBA members? Okay, good. If you are not, here's your pitch. It is your technical resource. It's relatively low cost per year, and it is a treasure trove of information. This is the Bible for the MBA, the Practical Brewer. At least it was when I got it in the late 90s. I think they still print books. Yes? Okay, good. In there, chapter 16 in my version is statistical management of processes in the brewery. So when I had a bunch of data and I was like, okay, cool, I've got this stuff, what can I do with it? I cracked this chapter open. I read it for about 4 minutes, fell asleep, rinse and repeat, right? I was never able to get through this chapter because it was all Greek to me. But I knew there was a clue in there. There's these fancy charts. Here's your control charts. Looks like it's got some data over time and it's got these control limits. What I didn't know is, what is that stuff telling me? How do I make it on my own? So that's what we're going to talk about today. So that was the clue. Unfortunately, like I said, math, statistics stuff, not my strong suit. So this is kind of my approach when I saw that data. This is one slide you can read through. This is how I approached those kind of math problems, right? I'm like, I don't even know what the heck this is. So to get past this, let's walk through the stuff. So let's talk about the what. So we talked about the data being, the brewery being data rich. So we're going to start with types of numeric data. When you are looking at your data sets from your brewery, whatever process you're trying to run, if it's your fill line, you're looking at fill levels or whatnot, you have either continuous or discrete data. Okay? Continuous data, that's data that usually you can measure with some sort of tool. Think of it as something on a number line, right? Units have standard sizes. You can usually cut them in half. So if I have an inch, I can have a half an inch. I can have a pound of pressure, I can have a half a pound. That is continuous data. It is different from discrete data or attribute data. So this is things that can be categorized. Things that are counted, the values, they can only take on certain values. Let me show you some examples that make sense. So continuous data. How many pounds of malt you've got in a recipe, your boil length in minutes, flow rate in gallons per minute, fermentation temperature, all of these things are continuous type data. Discrete data could be the number of complaints I had last year on a certain brand, right? The types of complaints. We had X amount of complaints on off flavors, X amount on oxidation. If you have a sensory program, if you do true to brand scoring, you know, I score 1 through 7, that is discrete data, okay? Day of the week, what yeast strain I'm using, what wort stream is it, all those type of things. So those are examples of continuous and discrete data. You may notice that ABV is on here both times. How can it be both, Jim? I'm glad you asked that question. That's a fantastic question. One of the reasons I want you to understand the difference between continuous and discrete data is sometimes we can unknowingly or knowingly record data as one form when we really need the other. When we're talking about control charts, we want continuous data. Okay, we don't want it to be discrete. So if I'm measuring ABV as far as a percentage, that's continuous. If I'm measuring ABV as go or no go, that is discrete. Okay, so as you're doing your data collection in the brewery, it may make a difference to you what you're going to do with the analysis. So you may want to consider what unit of measure I'm using to measure it. Same thing in fill volumes. I can measure that in milliliters. I can also measure that in pass-fail. Low fill or not low fill, right? Make sense? Continuous versus discrete? Okay. Just table stakes for getting into control charts. Real quick at the bottom, Frank Kerner from AB. I took a MBA class in 2002, and he put this formula up on the wall. Y is a function of X. When you are thinking about what data to collect in your brewery to monitor and control your processes, what this is saying is your output, right? I want good beer, I want a certain RDF, right? So you might measure RDF in your fermenters, except I don't directly affect RDF just by looking at the number. I affect it by pitch rate, temperature, all that kind of stuff. So the X's are the pitch rate, temperature, type of yeast, all that good stuff. The function of all that together gives you your output variable. If you're controlling a process, you might want to think about what are the X's. Because I'm not really controlling RDF, I'm controlling pitch rate, knockout temperature, all that, okay? So as you're deciding what data to collect, think about, is it an X or a Y, and is it continuous or discrete? Okay. Another table stakes for control charts is variation. All your data sets, all your process have some sort of variation. If you don't see variation in your process, you might want to look at a slightly different scale. Look a little closer. All processes never do vary. No two things are exactly the same. Day to day, we get different results. Okay? If you are going to improve in the long run or control your process, you need to understand, I believe, the source and type and quantity of your variation. That is part and parcel of understanding what's happening to your process. So determining the type of variation lets you decide what type of action is appropriate to take to make a significant and lasting change in your process. So there's variation, we need to understand it. To understand it, we need to be able to see it. So I think we're going to talk through, oh, look at that, we are. I reordered this last night, so you're as surprised as I am when the slides come up. It's fun. These are some of the tools you can use to start to understand, to visualize the variation in your process. So these are frequency plots. You frequently see these as a histogram, which is the bar chart there, or a dot plot. The only difference is one uses bars and one uses dots. What it's saying is, here's our height in feet in this example, and here's the frequency of how many data points I have, and it's just piling them up, you know, where they are. You can see here, this makes some sort of a shape. Are you familiar with a bell curve normal distribution shape? Probably heard that in the past. Remember back to high school? All right, that's what we're looking at. We're using a histogram, or frequency plot, excuse me, to look at the shape of your data, to just give a quick visual check to see, does this look normally distributed? The reason we care is control charts use and give you much better information when you have normally distributed continuous data. Okay? Word of caution, you can make a control chart out of any data. So you can make it out of non-normal data. It's just going to give you some control limits that may be pretty whack. And if you're making critical business decisions, that might be a little misleading. So you're going to want to check for normality before you bet the farm on your control charts. Like I said, this is the shape you're looking for. You're looking for something like this. In the wild, you are not going to see data that looks like this. Your data will be messier. I can almost guarantee you that, but it should look somewhat bell-shaped, okay? So when you have this normal distribution, why do we care about that? Why do we care if it's normally distributed? It's this thing here. If I pile up all your data, and we look in the middle, right? We've got the average here in the middle. What normal distribution, one of the characteristics of normally distributed data is you can calculate your standard deviations, right? These little sections coming out from the middle. And then you can estimate what percentage of your data should fall within those deviations. So if my data is normally distributed, 68% of all my data will be within one standard deviation of the average. Okay? That lets me predict over time where most of my data should land. So over here, you can see in the tails, right? About 4% of your data will be out here in the fringes, right? Out on the edges. Doesn't mean that you never have data out on the edges. It just means that should only be about 4% of your data is over in the tails. If you have a data set that's got like 20% of your stuff is way out on the edges, that is telling you this is not normal. Something's out of control. This process is not in control. It's not normally distributed. Does that make sense? Okay. So that's why we care, because now we can use a predictive model if we have normally distributed data. Unfortunately, we don't always have normally distributed data. Along with some of the messiness of our natural data, we also see other patterns. You'll see a long tail like this. That shape is normal when you have something that's like time-bound. For example, if I'm measuring days of fermentation, I can't have less than 0 days, right? So I'll have a pile up around 0, 1, 2, 3, and then it kind of tails off over here. This is a different distribution. So control charts do not work well with data that has a long tail like that. You might also see bimodal data. So this is like, hey, there's 2 humps here. It almost looks like if you separated those, you'd have 2 normally distributed populations. That's frequently the case. Sometimes that's data collected on the A shift versus the B shift. Sometimes it's louder tone 1 versus louder tone 2, right? But you might have 2 populations of data. So if you see this shape, you might want to kind of look and see, can I slice and dice this and find two different normally distributed populations? Okay. Again, if you have this non-normal shape, doesn't mean you have bad data. It just means that a regular control chart, off-the-shelf control chart, is not going to work for your application. When you see something that's uniform like this, all the values look like they're equally possible, something's happening. People are pencil whipping it, you've got the wrong scale. That is not something you see in nature. So this is not normal data. And then the other shape you'll see is whatever the shape of most of your data is could be normal, could be long tail, but you have these outliers here at the end. So if you have the outliers, this is usually like, go find out what these are, because if you know what they are, can say, okay, these two data points happened on a day when the power went off, right? That's not normally going to happen. You can maybe take those out of your data set and then look at whatever's left and say, okay, when the power doesn't go out, the rest of the data looks like it is normal, so you can use that for your control charts. So if you see outliers like this, what you want to do is go find out what they are and investigate. Rule of thumb, though, or word of warning, you can't just take them out of the data. Like, this shape doesn't look good. If you took those two out, that'd be fine. Don't do that. Right? You need to be transparent and honest with your processes. If you don't know what it is, it stays in. Does that make sense? Excellent. Math after lunch, good call. That's my favorite. Okay, so we've looked at kind of the data shape, right? And then we said control charts are continuous data over time. So now let's talk about what that same data looks like when you plot it over time. So back here, this is just piled up in a shape format. Now if we take that same data, plot it over time. So on a time series plot, time is always down here on the x-axis, and whatever you're measuring is the y-axis over on the left. In this case, they're doing widgets by day. So on a time plot, it marches forward over here. You've got your continuous data points. They're connected by a line, and they are in time order. Okay, so the first step, when you get your data, take a look, see what the shape is. This slide says the first step is to plot it in time order. Actually, that's usually what I do second. First, I look at the shape, make sure it's normal, plot it over time. The reason we do that is you can have data that the shape looks like it's normal, but if in time it goes like from high to low, like this, something's happening. So there are patterns you can see in time order data that you can't see when you draw it on a frequency plot, and vice versa. That's why we look at both. So you get your data, you plot it over time. Why do you do that? Here's a couple things you can see without applying any math or doing anything. You can see in this plot over here, there's some sort of process shift. You had data that was like bouncing around, you got some variation, then all of a sudden now it's bouncing around up here. That tells me something happened that day. Someone changed a setting, an ingredient changed, something happened, right? That's a shift. You can also see these outliers. If this is your, your production output, right? What is happening here on these days? These are Fridays. Everybody's like kicking ass because they want to get home, so we put out a ton more than normal, right? There could be some sort of a pattern that you can see from that. So outliers will pop when you plot them over time. If you then draw like a median in the middle of your data and say, okay, this is great, I'm going to find out what the middle value is and draw a line there, you can start seeing some other things. So when we talked about a shift before, there actually is a statistical definition for a shift. It's 8 or more points above or below the median. So this is something that you can use your data for. If someone comes to you with a chart and says, look, there's 3 data points in a row, we've got a trend, or the data has shifted, we've got to scramble the jets. You're like, hold on, give me a minute. It's not statistical proof of a shift until I have 8 or more, okay? So there's actually a definition for that. It doesn't mean when you start to see something in the data, you don't like zero in on it, keep an eye on it. But I'm not changing anything in our process until I see actual proof that there is something in the data. Because remember, variation is random. You could have 3 or 4 data points on one side of the median just by dumb luck, right? That's just natural variation. So shift is one thing you can see. Trends, this is the one that usually I have to not correct people on, but work with people on what is a trend and what is not. 3 data points in a row, not a trend, okay? 6 data points in a row, I'm 95% sure that there's something going on in the data, okay? Again, I don't let a spreadsheet or a graph tell me what to do with my business, right? The data is a clue as to what's going on. If I see 5 data points in a row, it's not like I'm gonna not do anything and be inactive and just wait until the 6th one comes, right? I'm gonna be watching this thing. Just because it's not statistical proof doesn't mean I don't pay attention, all right? But what the stats will do is tell you when you have a business case, especially if you're risking time, money, quality, this is when you should take action and get off your butt, right? The other thing you can see is a sawtooth. If you've got data that just goes up and down and up and down and up and down around the median 14 times in a row, something's happening. This could be that. If you go back here, said that you might have bimodal data. When you look at the shape, that's what this can look like when you plot it over time. So the A shift gets one thing, B shift does the other, A shift does this, B shift does this, right? So maybe you're measuring it differently over the different shifts, right? So you can see that in your data. All right, so that's time series plots, some patterns you can see just by putting that information up. When we talk about control charts, they add a couple things. Control charts draw a line through the middle of your data and use the average instead of the median. The previous plots use the median, which is the middle of your data. Control charts use the mean, which is the average, and then you calculate these upper and lower control limits. The word calculate is underlined here because this is the big thing with control charts. Your control limits, which tell you what's happening with your process, are calculated from your process data. They are not made up, okay? These are not spec limits. This is not, my customer wants it between here and here. That's different, okay? Control limits are calculated from the data and tells you what your process is capable of. What we're hoping is my upper and lower control limits fit nicely within what my customer will accept, upper and lower, whether my customer is the fermentation seller or the end customer, on the other end of the pint. But hopefully my process will deliver what they need. But those are separate lines. I put that chart later. I'll show you what that looks like later when they don't match. So what a control chart does, it says, okay, I've got the data, it looks normal, we've plotted it over time. Now we're gonna calculate upper and lower control limits. What they tell you is how much variation you can expect, right? We looked at that bell curve thing. We know 99.8% of our data is going to be within 3 standard deviations, right? And that's right around where those control limits are. So what that's telling me is if any point pops up or below, or above or below those control limits, that is like solid statistical proof that something is different, okay? So that tells you that. It gives you the expected range of variation based on historical performance, okay? Again, calculated from your data. We call control limits the voice of the process. It's your process telling you this is what I can do. That phrase is meaningful to us because we also have the voice of the customer. So voice of the customer would be your spec limits, right? What do they want? Voice of the customer says one thing, voice of the process says, here's what we can do. Your job is to match them up. I don't care if you are the end customer and say, I want my efficiency to be at a certain rate. Whoever that customer is, that's the voice of the customer. The data is the voice of the process. And like I just said, points outside of the control limits are another indicator of special cause variation, which we look at shifts, trends, outliers. Now we're adding those outside the control limits. So we've been talking a lot about the what part of control charts, right? Oh, we'll get to that next. So how you can calculate these control limits? Again, good question. Here's the intense math slide. If you would like to go ahead and calculate your control limits, you're more than welcome to. You get all your data together. You look at the range between each data point. You take those ranges, you average them out, you multiply them by some factor. You don't have to do this. Your statistical software will do it if you have that. If you don't have that, just use 3 standard deviations. For the example I'm going to show you later, I did it in Minitab, and then I also did it with 3 standard deviations. I plotted a bunch of real, RDF data, and it was within like 1%, 0.5% difference between using 3 standard deviations and doing the fancy calculations. If I'm doing something mission critical, I'm making millions of barrels of beer a year, I'm going to pay my stat guy to, do the actual charts. If you need to do this in Excel in your brewery quick, use 3 standard deviations from your data set. I'm going to show you how to calculate that. Make sense? Okay. So we talked about shape data, and over time, this just kind of combines the two. This is a screenshot from your practical brewer. So if you take that histogram, tip it up on its side, then line it up with the data over time, this is kind of what it's telling you. It's saying, okay, here's your average in the middle. Here's one standard deviation above and below. I expect 68% of my data points to be within that one standard deviation. If I expand it to 2, that's, what is that, 96% or so? And then 3 standard deviations would be 99.8% of all of your data. Okay? So that's what it's telling you. This is the slide I alluded to earlier. This is a control chart example. It doesn't have the line in the middle, it should, but it has these control limits up here. Again, these are calculated from this data, and then they've added, you'll see control limits, UCL, LCL, upper control limit, lower control limit. This adds upper spec limit and lower spec limit. That's the voice of the customer. If your data looks like this, my process is capable of between 30 and 36 on whatever they're measuring here, but my customer wants 34 to 31. I have a stable process that's giving me predictable data that is predictably not meeting my customer's expectations. So just because your data is stable and within your control limits doesn't mean it's necessarily capable of doing what you want it to do. So spec limits are important, the voice of the customer is important. It's just different than what control limits are. So what you want to do ultimately is compare the two and see. So in this case, I've got to do some work on this process to bring those control limits within what the customer needs. Make sense? Cool. Make sure you shout, scream, throw a beer, throw a 20 if you need me to slow down or have a question. Okay, so that's a bunch of the what. Those are all the elements you'll see when you start looking at control charts. I want to talk a little bit about some of the why. Why do I care about some of the stuff? We're going to talk about variation, your appropriate response to that, and what tampering is. So at the end of the day, like I said in the beginning, my initial question was, when do I need to tweak my process, right? I need some sort of tool to be able to monitor it, know when to act. I'm going to act based on what I see in the variation. So this is a key thing when you play this video later or whatever. Make sure we come back to this slide. Your types of variation. You've got common cause and special cause variation. Common cause variation is inherent to your process. It's always there. Your process is stable. You've just got the normal up and downs of everyday, process output, okay? Special cause is something that's unpredictable, irregular occurrences. It means if you have special cause, it means that your process then would be unstable, okay? Some examples of what causes these different types of variation. So you'll have common cause variation when you have things like lack of standard work. If everybody does things a little differently, you're going to get different results, right? If you're not training people to do your process the right way. If your system is either poorly designed or just does not have the wherewithal to produce within the range that you're looking for, that can be your cause of common cause variation. If you have process inefficiencies, all of those things affect everything that's going through your process. That is common cause variation. Sometimes you hear people say it's noise. Now look at the data, there's a bunch of noise. That's just that common cause variation, okay? When you have that, we're going to talk more about this in a minute, but your approach to addressing common cause variation is some sort of standardized problem-solving methodology. This is when you need to take your process apart and say, okay, what is it that's driving the variation? Isolate that root cause, figure out what to do about it, and then implement that. Special cause are things like, I had a machine fail, I had a tool broke, someone fell asleep at the machine. You've got an emergency shutdown, which may be driven by a weather event, okay? When you have special cause variation, those are things that they're unpredictable, they happen just once. When you have those, your approach to fix those is some sort of targeted action, right? Can I prevent the brewery from shutting down when the weather gets bad? Or when the power goes out? Can I prevent that? No. So just because you know what the special cause is doesn't always mean you can stop it from happening, but you can have a plan to recover. So at our small brewery, whenever the power went out, it was somebody's job to run around and shut off all the three-phase motors so that when the power came back on, it didn't come up on two legs and burn out a motor. right? So then when the power came back on, we'd go back through, turn on all the motors, okay, we're good to go. So we had a contingency plan to deal with special cause variation, even if you can't control it, okay? So our approach to special and common are different, and that's why it matters. So, special cause variation. If you have an unstable process that has special cause, what you need to do is find out quickly what happened in a timely manner. So if you are monitoring your process, you see a signal of special cause, it's important to find out right away what was different. If you get all your data from last month and you go back and you're like, oh, the second Tuesday of last month, there was a blip on the candy line. What was that? Nobody's gonna remember. That was 50 beers ago, right? But if I ask you tomorrow, what happened today? And you're like, oh yeah, the detail started acting up. I'm like, okay, now I know what it is. So try to collect that data as quickly as you can. Ask people what was different. Take, obviously quick response. This is firefighting. This is the stuff we do all day long in the brewery, right? That's special cause reaction. Again, if you can't prevent it, come up with a recovery plan. This is an example from the big brewery. Okay, so read an example. This is an actual control chart. This was brew house efficiency, BEI, I called it. This is indexed. So we made a lot of different brands. So all I did is took the historical average for every brand, made that 0. And then we plotted the efficiency for every brand against its historical average. So I could compare a porter against a Jetty Light, right? Which have vastly different efficiencies, but if I index them, they should all be 0. So we would monitor that on a daily basis. So this is, Jesus, is that 2010? It's been a minute. Holy cow. Sometime in 2010, we were monitoring, we got these, our statistical software will test for other special causes. So this number 2 error was telling me there's some sort of process shift. Took a look at this, went and asked the operators, what happened yesterday? Oh, the heat exchanger that was on the sparge line failed. Didn't think to tell anybody, whatever. Which meant that our incoming sparge water was cooler, which affected our ability to pull the extract out. Saw this, ran down to the maintenance department. We actually were sharing a KPI on brewhouse efficiency. So we're like, hey, there's money on the table. We're losing extract because the heat exchanger is broken. This affects our quarterly bonus. So if you guys can fix that for us, we'll get more extract, and then we'll make our KPI, and you'll get more money. So within a couple of days, they fixed the heat exchanger. And then over here, we had a number 6 error, which told me there is a process shift in the other direction, which was saying you fixed something is better. So that was our clue, that was our evidence that said not only did we fix the problem, but we probably made it better than it was before, because that thing probably hadn't been maintained. If you know the area I'm talking about, it probably hadn't been touched since the 80s. So we actually wound up better than we were before. So this was special cause, signal, quick investigation, reaction, and away you go. That's what we use this chart for. I posted this every day in the brewing office, in the room of the kettlemen were, so this is for the operators to see as well. Okay, so that's an example from my past life. That's all special cause variation. Common cause variation. You said if it's common cause variation, the process is stable, why would I want to fix it? If you go back to that slide that showed the customer specs not aligning with your process specs or your process output, that tells me I may need to work on a stable process. If you're going to do that, you're going to use something like a DMAIC approach. I'm going to show you what that is in a second. But you're going to take your process apart and look at the whole thing. Just fixing 1 day's worth of data isn't going to help if you have common cause variation, okay? Processes that are statistically stable require base process changes, and explaining the difference between 2 points of a process that's stable will not reduce variation. When a system is stable, telling workers about mistakes is tampering. This is something I'd really like you to take away. People see charts and they're like, hey dude, you were on the cattle yesterday and this is your data point. You're the worst of anybody that we saw, so get your shit together, right? When you do that to people, what you're doing is you're saying, this is common cause variation, which by definition means you didn't do anything different. And when you put them on the hook for that and make them try to explain it, they will find a way to explain it to you, okay? Usually what you're doing is you're motivating people to do the wrong thing. They're like, oh, I'll make sure that number's never below that line again. And they'll do something you don't ultimately want them to do, okay? This is why the reaction between special cause and common cause, I'm really passionate about that. It's one of the central failures of leadership is when we're asking people to explain common cause variation. You see this in budgeting all the time, right? My monthly spend is up and down like this. Oh, last year you spent way too much, you were above the average, you're fired, right? If it's just that normal up and down, now you're motivating people to say, well, I'm not gonna buy that extra, lot of malt this month because it'll look like my budget's off. And then next thing you know, you run out of something you should have had, then you expedite it, you run out of the right beer or the wrong beer. It's behavior like that that drives waste into our system. So this is why, to me, process control is so valuable because you can get some of that stuff out. So, reacting to common cause variation. If you have to improve a stable system, you use some sort of approach to look at the whole thing. We do this with project work. It's the DMAIC cycle. You define what the problem is, measure what your current state is, do some analysis to find your root cause, your true root cause, okay? Figure out what you're gonna do to fix it. That's the I for improve. And then you put in a control plan to make sure that this thing never happens again. Okay, it's whatever system you use or just thought process, it's that thoughtful approach to taking your process apart and improving the whole thing. I promised Paul we wouldn't do any pitches. We're at booth 85. If you want to talk about DMAIC, I'll talk to you all day about that, how that does. If you do have a process that's under control that you want to improve, one of the things you can do with your data is just start doing a couple of these things. You can stratify your data and say, okay, is it better when I make this beer versus that beer, right? So you can kind of stratify by different factors to see if you can find what's driving the results and the variation you're looking for. You can disaggregate it, which is taking it apart it's very similar to stratification, taking the process apart by parts, right? So like if I got an issue with the can line, is it the decal, is it the palletizer, or is it the filler, right? So concentrate on that part in the middle. It's not big. And then the other thing you can do with your data is just experiment, right? Just see if you can turn the thing on and off. I'm gonna try something, we're gonna do it for 2 days. If it changes the data, I might have a clue that I found root cause. The 3 rules for experimenting with your data when you're messing around with your process is it's gotta be safe for the people that are doing it. So physically safe, you can't put any people in danger, obviously. Let's not remove any guards and do any of that stuff. It's also got to be politically safe for people. If you let somebody monkey around with your process and they get bad results, they can't have their boss coming to them and then yelling at them because they did an experiment. So you make sure you have sanction to mess around with the process before you do it. Okay? So it's got to be safe for the people doing it. It's got to be safe for the customer. If I'm going to screw around with my brew house, I'm not going to do it on the one contract brew that my customer is counting on, right? I'm going to make sure that they are protected. I will experiment with my process on my own time. And then it's got to be economical. As long as it's safe for the employees and the customer and it doesn't cost $1 million, then just try it. Try it running this way. If the data is better, okay, let's keep going down that path. If it's not, try something else. So if you're trying to improve a stable process, those are a couple techniques that you can use to try to get at the root cause. And then let's talk about what happens when you ignore your special and common cause. So tampering is when you are messing with a stable system. It's the inappropriate reaction to common cause variation. You just see the normal up and down, and you're like, well, I'm going to mess with this and see if it gets any better, just for the heck of it. If you tamper on a stable system, generally what happens is you start to amplify your variation. And if you just let it go, the modeling shows it's usually around 41% increase in variation. So if you take something that's stable, just start messing with it willy-nilly, you usually wind up making it worse by about 40%. Okay? This is why in God we trust, everybody else brings data. If you want to mess with my system, I want to see the data that says, okay, we have a signal here, we know what the baseline is, let's go. Okay? So now that you know that, you'll never tamper again. You're always going to ask people, is this common or special cause? Show me the data. So I'd like to see the data, Jim. How do I get that? Well, here you go. Collect your data, calculate some basic statistics, draw a histogram, create a control chart. I'm just going to walk through doing this in Excel real quick so you can see. These are the fancy little transition there. That's top secret. You can't see that previous slide. Yeah, those are the steps. That's your little bookmark. That's your 5 steps to make one. All right, getting your data. So first thing is collect and clean your data. So first thing I'm going to do is I'm going to get a data set. I'm going to go through and just make sure nobody put this one has 7 extra zeros in it, or somebody messed up, put a decimal in the wrong spot. You might want to take a minute and clean your data just to make sure that it is valid, right? Look for any fat finger mistakes or formatting goofiness. You're going to put whatever your value of interest in this example, we did RDF, put it all in one column, make sure it's all formatted the same way. I'm a big fan of Microsoft Excel tables. If you don't use them, I love them. It lets you create a table. Every time you tab over, it starts a new record. More importantly, it copies all your formulas over, updates the formatting, ensures that everything is formatted the same way. But regardless, put them all in one column. Put some sort of observation number or date, some sort of time order data in the next column next to it, right? You're going to want to have this over time. We said the time is one of those patterns you're going to look for. So whether it's the observation number, the date, whatever. So you got those 2 there, paste them all in. You want at least 25 data points, okay? I'd like you to have 100. That's what you're looking for, something like that. But with continuous data, 25 data points will give you an idea of normality. Anything less than that is not quite enough data. Once you got them all in there, then create a histogram. So select just that one column. You can insert charts. Excel has nicely put in a couple statistical charts. One's a Pareto, the other is a histogram. Select histogram, it will draw this for you. Okay, you can do it manually, but that's a histogram and it's built right in. If you want to play around, if you right click down here on the axis, you can change the number of bins. I think the default here is 6. I usually like 10. It gives you a little bit more visibility, or resolution is the number I said earlier. So you can play with the formatting or whatever, but basically that's your shape. So now just take a look at it. Does it look normally distributed? If it's way off, you're going to need to do some digging. If it's roughly bell-shaped, then we'll move on to the next step. The next step for me is to calculate some basic statistics. Your package will do that for you. I'm going to show you a bunch of formulas. I think this is available afterwards, so if you need to take a picture of it or stop by the booth or drop me a card before you leave, I'll send you like an Excel document. This is what I'm calculating. The highlighted ones are the ones you have to do to make a control chart. Everything else is just kind of bonus. I'm going to calculate what the average is. I'm going to calculate the median, just so you know, in normally distributed data, the mean and the median are usually pretty close together. If they're pretty far apart, that's a clue that it's not normally distributed. Okay? That's why I calculate both, but you need the mean for your control chart. Skewness and kurtosis. These are statistical things I'm not even going to bore you with. It's about the shape. You can plug these formulas in, just select your data range, plug those 2 formulas in, and it's going to give you a value. If it's between -1 and 1, you can assume normality. Okay? So if you run kurtosis and it's -4, that is not normally distributed. So if you just want a quick statistical check, run those 2 stats. Okay? Then there's your formula for standard deviation. Calculate that on the same data range. And then your upper and lower control, just multiply that by 3. So times +3 is your upper control limit, times -3 will be your lower control limit. Again, the other formulas for actually calculating as far as the stat guides go is in here. So if you want to get more precise, you can. But that's your quick and dirty way to do it. I usually just make a table, put all that stuff in there. Now I have the mean, upper and lower control. I'm going to copy those values and use them as a static value back in my chart. So here's the observation number in the RDF that I put in earlier. I'm going to create a mean, an upper, and a lower control column, and I'm going to paste those values in as absolute values. So these numbers don't change, right? So once I say that the average is 87 and my upper and lower 93 and 80.8, copy those down as absolute values against, on every record here. And now you have enough to run a 2D line chart. So again, just go in the chart section, insert, select RDF, mean, upper and lower, run your 2D chart. Then you can play around with the formatting. It'll draw you a chart with the upper, lower, and middle. You might want to color them. You might want to put in the markers. That's what I did here. So this is right from Excel. This is the data I used for the example. I made these lines a little smaller. I added these markers. I changed these to red. but that's your control chart. Do you see any signs of special cause here?
No.
Correct, yes. Do you guys know how long you're supposed to wait after you ask an open-ended question? That's a good one. 10, doesn't matter. Yeah. Supposed to wait 10 seconds. That's long enough for people to get uncomfortable and like blurt out the answer because they're like, okay, I can't see it anymore. I don't see any signs of special cause here. Now, be aware, some of the more sensitive tests that we talked about, some of the process shifts, like is this, 6 or 7 on one side of the line or not? Those, Excel does not figure that out for you, right? If you're interested in that, you might want to, learn those rules, and you can do it manually, or send your data much more easily. Send it to your data nerd friend and say, run a control chart for me through your software. Yes, sir.
ASQ has a bunch of tree and control chart templates
Nice.
that are do X, Y, R, bar, all that good stuff.
Man, I wish I called you last week. ASQ has templates for all of this stuff. Fantastic. Another fine organization to be a part of. And another good reason to do that. Now that you know what they are, and I hope really my purpose in what I put together today was for you to understand what you're looking for and why. How to do it, you can Google. Sounds like ASQ's got some resources. You can figure out how to make the things go. But what you're looking for is it meaningful? Is it a meaningful signal? Is it special cause? Is it common cause? Should I act or should I not? Okay. Okay, next steps. So you've done all this. You're like, cool, my data looks stable, I'm good to go, what do I do now? You can use this now to monitor your process. So what I would do at this point is, if your process is stable, you keep the same upper and lower control limits, now just add to that data set. Every time I ferment a beer, I'm gonna take that RDF, I'm gonna plug that in there along with the observation number or the date, whatever it is, and just keep adding to that chart. Don't redraw your limits every time you make a control chart, because what you're doing is saying, okay, based on this data, what is my control limits? And then tomorrow, what is this data, what are my control limits? If you do that every day, your control limits will drift with your process. So what happens over time is if your process drifts, your control limits will go with them and you'll miss those signs of special cause. So keep your control limits static until you have some reason to change them. Why would I change them? I did a process improvement project and I changed the process. So now I'm going to redraw the control limits as a new baseline. Or I bought a new brew house, or whatever. If there's some fundamental change to your process, some special cause that is now going to make your process shift, redraw your limits and go from there. So keep your limits static, add to your data set, monitor your process. When you see special cause, find out what it is, take action. Keep making sure that your control limits for whatever your process is match what your customers are looking for to make sure that it is capable. If it is not capable, you're going to need to do a larger process control or process project. Okay. Like I said, I don't usually talk this much in one way at one time. So just to summarize, we talked about 2 different types of numeric content. Make sure you have continuous data if you are working on a control chart. Discrete data, if it's a number, it's going to draw you a chart, but it's not going to tell you what you want. If you're looking for continuous data, we know that variation is to be expected. The question is it too much or not enough? Your control limits are the voice of the process. It's your brew house telling you what it can and can't do. There are 2 big types of variation, common and special. Tampering is when you act inappropriately in reaction to either of those. You need to understand variation in order to respond appropriately, and your frequency plots will show you shape of data, shape, center, and spread, and your individual control charts will plot normally distributed continuous data over time. Couple things. Like I said, all of that stuff is in here, along with all sorts of other good stuff. Please avail yourself of the MBA stuff. They have a booth here at 92, I think it is. If you're not an MBA member, stop by and see those guys. It's a great organization. We have a meeting next week. Is it at your place?
Yeah, it's at my place. Yep.
Next week at Strangebird, so come on over. So we took some of the slides and stuff from there. Like I said, a lot of the information I'm talking about is in there. We do the Greenbelt training, which is the DMAIC process and all that. So if you want to know a little bit about process improvement, come see us at the booth. Or if you want to drop me your email or take my card, I'll send you the Excel stuff that I used for the presentation. Took some stuff from Minitab, which is statistical software. There's other stuff out there. Jump is one. There might be some lower cost statistical software if you're into that. And if you need to know how to do it in Excel, just jump on YouTube or whatever, Google. You fire up your Google machine. There's a million videos on how to make these things. That's it. I wanted to make sure that we were done early so I didn't math you to death. Questions about usage, making anything on control charts? Sir, ma'am, yes.
If you have a small brewery and so you are brewing multiple batches a day, multiple times a week, it's going to take forever to amass enough data to actually exfoliate.
Yeah.
How do you recommend addressing something like that?
So where we can, so the question is if you're real small and don't have a lot of data every day, how do we get enough? One of the things they do, like when I was brewing at the small brewery, right, we didn't have enough repetitions of certain brands. So I would do things like I would find a discrete variable, like bed loading. So everything that had a certain amount of grain per, or malt per square meter in the lauter ton should basically run off the same. I don't care if it's, what brand it is, it should basically run off the same. Those were all grouped together. You know what I mean? So sometimes you can kind of group things together and say, even though they are, different word streams or whatever, they should perform the same at this part of the process. So wherever I can do that, I would do it. It might be a matter of, again, discriminating between what the X's and Y's are. Like I only have so many outputs of the beer, but I do have workflow throughout the whole runoff. Like I might have 25 data points within one run, so it might be a matter of taking your process apart. Good question. Yeah.
So if you're just starting out with it, where in the brewing process would you start? Like if you could only do 3, would that be like
Sure.
completion or
Yeah.
efficiency?
I'm going to give you the high price consulting answer. You know what that is? It depends, right? It depends on what's most, that's the first question. What's most valuable to you? If you're like, I'm bleeding time, like I just don't have enough time to get to everything, then I might be looking at my process like, where am I taking too long? Maybe I'm tracking that to see if that's an issue. If I have fermentation issues, RDF was my example for a reason. That's one of the things I was constantly, to me that gets down to, brand, sensory and all that. So I'm definitely watching that. Me, it was always extract in the brew house, extracts money. So just making sure that the brew house was running correctly, people were following procedures. You could see that in the data. When people start, I'm going to run it off this way, you're like, boop. I saw that in the data. It was either much better, and I didn't hit on this earlier. It's not always a problem. Sometimes your special cause signal is like, it's way better when Dean runs it. So what's Dean doing different than anybody else, right? So let's find out what that root success is, do what he's doing, right? Could be that he's cheating. That's probably most likely, right?
I think you yelled at me more than once for that.
Yeah. Does that make sense? I know it's a depends answer. I'm looking at extract and usually just fermentation performance. Yeah. Good question. Yeah. Anything else? Yes, sir.
It's amazing.
Thank you, Emil, for coming. No, I'm sorry.
It really boils down to there's when there's money on the table with extract, when you're going through, and even if you just pick 3 things to start checking, and you're looking at your boil off, you're looking at your efficiency, you're looking at your IBUs, and that's all you track. Start somewhere, shit that in to shit that out. When you don't track it properly, you're not going to get what you need to get out of it. And you can turn it into something super simple and just do OG for the first time. And you can look at when we did the MBA group, and you can look at your SIV analysis, and you can improve that, and it's money on the table that stays in your pocket, which is crazy. So again, a little plug for the MBA. It's $179 a year, and you have access to everything that has ever been published in the MBA. So it's absolutely amazing. It's one of the cheapest things you can actually search for. You can search for anything on the MBA. You can search for anything. Jim's been yelling at me for 24 years about stuff. But shit that in, shit that out. And if you're not tracking anything, you're actually leaving money on the table. So.
The other one that we didn't hit on is supplies. So, you guys get certificates of analysis with your malt. I would plot coarse ground as is and just make sure that stayed constant. And beta glucose was the other one. Like Man, we're having a hell of a time with runoff lately, and then, if you look at your incoming beta gluons, now normally if they're giving you a C of A, they're on their ball and it's usually in control and it's not, you know ahead of time if your supplier is on the ball, but I can be tracking those and verifying, like, oh, it looks like something happened in May, so it's the old blame the maltster thing, right? So this data will allow you to either confirm or deny that. Separating fact from fiction. So yeah, incoming raw materials is another place I use that a lot.
And we get into process control charts for package oxygen for quality,
Yeah, 100%.
and then we wind up going back to working with the mixing process. There's a lot of applications that make save money, that makes quality improvements.
The more we talk about this, the more I remember. I've been out of brewing for a little bit. It was fill levels too. Like, you're required to be compliant, right? With plus or minus 5% over 3 months, whatever. We would sample, get your stat friend to help you come up with based on our typical canning run, how many cases you run, what is a statistically valid sampling plan? And we would sample, I think, 5 times over the course of the run, and we would plot the average and the range in between them all to know if, like, we had a fill head problem, right? When do we adjust the problem, filler or not? If you can, how many times have you blown things up because somebody starts messing with the settings, like, well, I think it runs it over here. And next thing you know, you've got a million low fills, right? This, if you have stable stuff, it tells you when to adjust. Do you have a question, or were you waving, Mika?
I was waving.
Oh, okay, good.
So small breweries, you don't have enough data, like you said, OG is easy, thing to look at, yield, brew batch. There's a lot of things you have data on the record. So,
Yep. So, dissolved solids, we used it to make sure that the boiler was always performing well, right? So taking that dissolved solids every day and charting that, I could see when, oh shit, we need to do something or flush it, or I can't even remember now what the thing was, but we had it on the outside of the boiler room door and we hit it every day. Because when that thing, if you've ever lost a boiler, you don't ever want to do that. So we use that because that was a critical, that's the lifeline for the brewery. So we just monitored that every day and make sure the solids were just not.
And everybody's already doing this. Everybody's tracking OG, you just gotta put it in the right spot. You guys are all doing the work already.
Yeah, it goes back to that first slide. We're rich with data. I got a bunch of it. Spreadsheets full of stuff. It's just, what do we do with it? It's cool to have it. It's even better when you can turn it into action or prevent yourself from taking an action that ultimately you don't need to do. Well, if there's no other questions, I'll give you 4 minutes back. We're good.
Well done.